everyone, welcome to my channel ECE Scholastic. I'm Jasmine. I welcome you all to the 9th session of Discrete Time Signal Processing of Unit 1 Discrete Fourier Transform. In today's session, we are going to learn fast Fourier transform, types of fast Fourier transform and basic butterfly structure of this fast Fourier transform. Now let's start the session with fast Fourier transform. In previous sessions, we have discussed about discrete Fourier transform, that is DFT, right? Now we are going to see about fast Fourier transform. So why we are going for this fast Fourier transform? From the name itself, we can easily understand that in fast Fourier transform, the Fourier transform can be performed in a very speedy manner on comparing to this discrete Fourier transform. In discrete Fourier transform, in order to find out the sequence, the final output, that is either x of k or x of n, okay, it will take a tedious process or the steps is a very complex one. But with the help of this fast Fourier transform, we can reduce the number of steps as well as the complexity and also the time delay. The fast Fourier transform uses a divide and conquer approach, which means the given sequence, either it may be x of k or x of n, the given sequence can be completely divided into a set of smaller sequences which follows some stages of computation at different stages, and a final output is obtained, which is a very simple one when compared to that of DFT. And also it reduces the computational complexity. So the FFT has a major advantage over DFT in terms of computational efficiency. As you know, we are using DFT to transform the time domain signal to a frequency domain signal or vice versa using IDFT concept, right? So the DFT and IDFT are combinedly used to perform these transformations, correct? But when we are writing the formula for DFT, that x of k is equal to summation n equal to 0 to n minus 1, x of n e power minus j 2 pi nk divided by capital N, correct? So here we are having a multiplication of two variables and also an addition of a number of variables, correct? So the DFT follows both arithmetic operations, that is addition as well as multiplication. Okay. If there is a complexity, then the complexity will be in terms of addition and multiplication. Correct. So now we are going to compare the complex addition and multiplication between this discrete Fourier transform and fast Fourier transform. In discrete Fourier transform, the number of complex additions will be equal to n into n minus 1 and number of complex multiplications will be equal to n square, where n is nothing but period. Okay. And in fast Fourier transform, which can also be called as radix 2, which means the logarithmic base is 2. Okay. So here the complex addition formula is n log n to the base 2 and complex multiplication formula is n by 2 log n to the base 2. With the help of these two formulas, we can find the computational efficiency of FFT. That is complex addition. The computational efficiency is calculated using the formula complex addition of DFT minus complex addition of FFT divided by complex addition of DFT into 100, which gives the percentage in terms of addition. Okay. And the complex multiplication formula is complex multiplication of DFT minus complex multiplication of FFT divided by complex multiplication of DFT into 100%, which gives the percentage for multiplicative operation. Okay. Now, let's solve a problem with the help of these formulas. Our example 1 is calculate the complex number of additions and multiplications required in calculation of DFT using FFT algorithm with 1024 point. So in the question it is given n value as 1024 can be written in terms of 2 power as 2 to the power 10. Okay. Now we are going to calculate the complex addition and multiplication values for DFT. That is the first step. And the complex addition and multiplication values of FFT, that is our second step. Finally, we will be calculating the computational efficiency. Okay. So I'm going to start with DFT, that is direct computation. Here we know the complex addition formula is n into n minus 1. So I'm going to substitute the value of n as 1024 into 1024 minus 1. On calculating, the value will be equal to 1047552. Okay. Now I'm going to find what is the answer for complex multiplication. The formula is n square. So this is equal to 1024 the whole square. The answer will be 1048576. Okay. So DFT part is over. That is our first step is over. Now I'm going to find the FFT part. I know the complex addition formula for FFT. So the complex addition formula is equal to n log n to the base 2. Here n value can be written as 1024 into log of 1024 to the base 2. I'm going to write this 1024 in terms of 2 to the power. So it is 2 to the power n. As you know, log m to the base m is equal to 1. And also log m to the power n can also be written as n log m. Right. So on using these two formulas, I will get the answer as 1024 log 2 to the base 2 is 1 and power can be taken to the front side. So multiplied by 10. This is equal to 10240. So this is the addition value using FFT. Now I am going to find the multiplication value. I know the formula for multiplication as n by 2 log n to the base 2. Right. N by 2 is 1024 divided by 2. Log of n value is 2 to the power 10 to the base 2. Okay. So I will get the answer as 512 into 10. That is equal to 5120. Okay. Now I am going to calculate the computational efficiency. So I know the computational efficiency formula, right? Now I'm going to find for complex addition. So for complex addition, I know the formula. What is the formula? Complex addition of DFT. So what is complex addition of DFT? We got the value as 1047552, right? Minus complex addition of FFT. So what is the complex addition value of FFT? 10240. Okay. This divided by 1047552 into 100. Okay. The value will be equal to 99.02%. Okay. In a similar way, I am going to find for complex multiplication. So my formula is complex multiplication of DFT. The answer is 104576 minus the complex multiplication of FFT is 5120 divided by complex multiplication of DFT, that is 104576 into 100. So this value is equal to 99.51%. Understood? So that's all about the computational efficiency calculation. Before going into the types, let us know about the concept of computational stages. Usually the endpoint is the period point, right? So the endpoint is represented using 2 to the power m in FFT, specifically in FFT. So which means 2 to the power m means we will be having m computational stages. Okay, for example, let us say the value of n is 4. So it can be written in 2 to the power as 2 to the power 2, right? From this we can say that particular sequence will have 2 stages of computation. Okay, 2 stages of computation. If we say n value is 8, then in terms of 2 to the power, we will be writing it as 2 to the power 3, right? So here we can say it has 3 stages of computation. So the number of computation stages depends upon the value of m, and it is a must condition for FFT. Now let's see about these types of FFT. FFT can be broadly classified into 2 types. One is decimation in time domain and the other one is decimation in frequency domain. In a short form, it can be called as DIT method and this can be called as DIF method. In decimation in time, the complete sequence, let's say that our n value is 8. Now, this 8 elements in the sequence can be computed as 4 sets of 2-point sequences. 4 sets of 2-point sequences, that is our first stage. And the 2-point sequences will take a form of even sequence and odd sequence. If you see, these two are the even sequences and these two are the odd sequences. Okay. So, first stage is over. And in the second stage, it will take 2 sets of 4-point sequence. All the even sequence will come to one side and all the odd sequences will come to the other side. Okay. And the final stage is a single set of all the 8 elements. Okay. As a whole, we can say that decimation in time follows 2-point, 4-point and then 8-point. Understood? That is, the 8-point sequence can be carried out as 4 sets of 2-point sequences. Second computation is 2 sets of 4-point sequences and third one is a single set of 8-point sequence. So what actually will happen in frequency? It will be a straight reverse of this. So initially it will be an 8-point sequence. Okay. Next it will get splitted into 2 sets of 4-point sequence. Next, it will get splitted into 4 sets of 2-point sequence. Understood? Now let's see the basic butterfly structure for radix to DIT and DAF. Here I am going to consider a 2-point sequence. So we will be drawing a basic butterfly structure for a 2-point sequence. Okay. As I said, 2-point, we will be having 2 inputs. Let us take the 2 inputs as A and B. Okay. I'm going to draw the butterfly structure for this. So I have represented a line for the input A as well as a line for input B. So the multiplier for the line A will be 1 and the multiplier for the line B will be -1. Understood? So wherever we are giving this -1 weightage, there we need to add a twiddle factor Wn to the power k. Now I'm going to cross these 2 inputs. So this structure looks like a butterfly structure. Now let me say that the output of the first line A is capital A and the output of the second line B is capital B. Okay. So this point is your output point, that is first output point. How can you write the formula? Here the elements in the same line we are going to multiply and the elements from the other line based upon the sign we will add or subtract. Okay. So here A into 1 is equal to A and this line B into Wn to the power k. So that is positive, right? So plus B into Wn to the power k. So that is our A formula. Understood? In a similar way, how can we write this B formula? So B is equal to, first line is A, and here B into Wn to the power k into -1. So it can be written as minus B Wn power k. So the formula will be like this. Understood? Now let's see what is the basic butterfly structure for DAF. Here also we are having 2 input sequences A and B. So the follows the same concept as that of the previous diagram. Here we are having +1 and -1. And wherever there is -1, we will be giving the twiddle factor Wn per k. The only difference is in DIT structure, the twiddle factor is given at the input side, and in DAF structure, the twiddle factor is given at the output side. Okay. Now I am going to cross these 2 inputs. So my first answer, A is equal to, here this point, what is my answer? A is equal to, A into 1 is A. Okay, and here plus B. So my answer is A plus B. Okay, and here what will be my answer? So the first line, at this point my output is A and this line is B into -1, that is minus B. Correct? And which is multiplied by, we are having a twiddle factor at the output side, Wn to the power k. So the formula for B will be like this. Okay. Now I hope that you understood what is the major difference between this DIT and DAF. So in DIT, twiddle factor will be at the input side, and in DAF, the twiddle factor will be at the output side. Okay. As I told you, we have the endpoint values as 2, 4, 8. It goes like this, but we will be concentrating only on these 3 values of n. So if we have the value of n as 2, then we will have a twiddle factor W2 power 0. Okay. If we have a value of n as 4, then we will have the twiddle factor as W4 power 0 and W4 power 1. Okay. And if we have n value 8, then the twiddle factors will be W8 power 0, W8 power 1, W8 power 2 and W8 power 3. Okay. Now let me tell you what are the values of all these. For 2-point, as I told you, we have twiddle factor W2 power 0, which is equal to 1. And 4-point, we have 2 twiddle factors W4 power 0 and W4 power 1. So the W4 power 0, the value is 1, and W4 power 1, the value is -j. Okay. And for 8-point sequence, W8 power 0, the value is 1. W8 power 1, the value is 0.707 minus j 0.707. W8 power 2, the value is -j. And W8 power 3, the value is minus 0.707 minus j 0.707. How we are writing these values? No, Wn is nothing but e power minus j 2 pi by n. Okay. If I consider W4 power 1, then I can write this as e power minus j pi by 2. Correct? If I apply the value of n as 4, I will get e power minus j pi by 2, which is equal to cos pi by 2 minus j sin pi by 2. Cos pi by 2, the value is 0, and minus j sin pi by 2. Sin pi by 2, the value is 1. I will get the answer as minus j. Okay. If I consider W 8 power 2, what will be my answer? E power minus j pi. Here I am having 2, so I will take it as 2 divided by 8. So this 2 and this 8 will get cancel each other. I will get minus j pi by 4, that is equal to cos pi by 4 minus j sin pi by 4. So pi by 4 is nothing but 1 by root 2, right? 1 by root 2 is 0.707. So I will get the answer as 0.707 minus j 0.707. Understood? This is how we will be calculating. Or in general, I can say W n power nk is equal to e power minus j 2 pi nk divided by capital N. So instead of nk, we will be applying the values 0, 1, 2 or 3 based upon the point. Please by heart all these values. Next is, let me tell you the major differences between DIT and DIF. In DIT, we know one difference. What is that? The computational stages will be of point, 4 point and 8 point. And in DIF, the computational stage will be as 8 point, 4 point and 2 point. Okay. And the second point is here, the Tudel factor will be given at the input side of the sequence, correct? Input side of the sequence. And here the Tudel factor is given at the output side of the sequence, correct? Now the third point is, input to the DIT is in bit reversed order and output is in normal order, okay? Bit reversed order and output is in normal order. And here the input to this DIF is in normal order and the output is in bit reversed order. Okay. How can we say this normal order and bit reversed order? Let us consider an 8-point sequence. So my sequence will be 0, 1, 2, 3, 4, 5, 6 and 7. I am going to write the binary equivalent for these 7 values. That is, my binary equivalent for 0 is 0, 0, 0. Binary equivalent for 1 is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 5, 1, 1, 0, 1, 1, 1. Okay. Now I am going to reverse this. Reverse this in the sense 0, 0, 0. 0, 0, 1 can be written as 1, 0, 0. 0, 1, 0. 1, 1, 0. 0, 0, 1. 1, 0, 1. 0, 1, 1. 1, 1, 1. Understood? So this is nothing but x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. Okay. Now what is the decimal equivalent for this binary? 0. And for this 4, this is 2 and this is 6. This is 1, this is 5, this is 3 and this is 7. My sequence will be like this: x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. This is what I mentioned here: 0, 4, 2, 6, 1, 5, 3, 7. Right. My output of DIT is normal order, which means x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. That is, we are transforming x of n to x of k. Okay. If we consider this DIF, input is a normal order, which means x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. But the output is in bit reversed order, which means x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. Understood? So this is the major difference between DIT and DIF. So with this, today's session is over. In the next session, I will explain about the general derivation of DIT followed by general derivation of DIF. Later, we will solve the problems under DIT and DIF. Hope you understood all the topics that we discussed today. Thank you. If you have any queries, please post me here so that I can respond. Thank you. Thank you for the patience. Have a great day.